Welcome to Industrial PLC Application, and this video is part of the First Look series, Path of Continuous Logical Flow. The one thing that both relay logic and its descendant ladder logic share is continuity. They both have to have a clear path of resolution in order to energize a circuit or logic. With relay logic, we need to observe inputs like switches and watch outputs to see if they are energized, since electricity is invisible. We can also use testers and check continuity. With ladder logic, we can view the logic flow using software when the PLC is connected and the program is running. Great in theory, but we need to look closer at ladder logic, especially if we consider it more than a simple run of logic. With relay logic, power is always present at all parts connected to the rails. The moment a contact is closed, all parts of the logic related to that contact are energized equally at the same time. This makes the logic asynchronous, each part working when called upon, not in a regulated order, that is to say, one after another progression. With PLCs, each rung is evaluated one at a time, starting at the top rung and resolving the logic from left to right. After completing a rung, the PLC goes back to the left rail and examines the next rung of logic in order. If the logical connections between the elements are true, then there is a logical path of continuity, and the output can be energized as shown with the top two rungs. As each rung is resolved, the PLC places a 1 for a complete logical path to an output, and a 0 for an incomplete logical path. But before the real-world outputs are energized or de-energized, all rungs of logic in all programs must be resolved, and under normal circumstances, the last written value will be executed, and the outputs are energized or de-energized. However, there are two unique properties about the PLC and its process of recording output values. One, each recording of a 1 or a 0 overwrites the existing value, even if the value is the same. And number two, the outputs aren't immediately turned on, and associated contacts do not immediately energize their outputs. A continuous path of logical continuity is one where the PLC detects a series of connections of instructions that begins with the left-hand power rail through any viable path of true instructions to an output or executable instruction connected to the right power rail. So let's begin by looking at a very simple rung of logic. We have one contact and one output coil. Right now, the input 00 is not true, so there is no continuous path for logical solution. If I energize 00, then the whole rung becomes true. If I de-energize it, I no longer have a path of continuity. Logical continuity can differ from relay logic. In the above example, a normally closed push button allows for electrical continuity, and therefore the output run_1 is energized. But with the PLC, the same logic cannot use a normally closed instruction. Here we have the same rung of logic in PLC as opposed to relay logic. We know it's a normally closed push button, so we're using a normally closed instruction. However, the run is not energized. This is because this instruction tells the PLC to go look for the absence of voltage, a 0. It found a voltage, as can be shown by the red lettering, which is not the correct response that it's looking for with this instruction. Therefore, it's false, which means the output must be false. In this instance, the program requires there be a signal or a voltage at the input DI_03. If the normally open contact is selected, the programmed rung works. This particular rung is a bit of a puzzle. We have a stop push button, and stop push buttons are a normally closed set of contacts, and yet in this particular rung we're using a normally open instruction. They seem to be conflicting, and yet we still see that there is logical continuity from our left rail through our stop switch to our run. This is because the instruction is saying look to see if there's a voltage. If there is a voltage at that terminal screw, then you must accept that as having logical continuity and carry on with the rest of the rung. In this case, resolve it by turning on run_1. Keep in mind, we can look at any variable in its current state or value in one of two ways. Is the variable true, or is the variable false? Moreover, we can then use these two different states depending on what we need to control. Here we have the digital input 3 connected to two different rungs. On the first one, the instruction says check to see if there's voltage, which there is. This provides logical continuity, and therefore run 1 is on. The second instruction says go look for an absence of voltage, and if it's true, turn the rung 2 on. But there is a voltage there, therefore that instruction is false. There is no logical path of continuity, and therefore run 2 is off. As long as there is logical continuity, or the absence of logical continuity, you can write logic to take advantage of the difference and control automation. Using the opposite state than expected to arrive at a different outcome is called not logic, and at times it can help resolve the ambiguous state. As we mentioned, it's not the contact that you use, and it's not even the value of the contact. Is how do you want to interpret it? We have two rungs here, both examining our stop push button. The first one, we're using the normally open look for a voltage, which it finds, and it turns on output digital output 01. E-stop is okay. The second one says look at the same stop button and look for a 0. If you don't have it, don't energize the rung. But if we change the state of the stop, now we know that the stop has been depressed. So we can use both sides of any contact. We can use a 0 or a 1 anywhere in our program, depending on how it's to resolve our logic. Alright, so we have an air cylinder, and it has two cylindicators, which is a special proximity switch that will look internally at the position of the piston, making it going forward and back. And right now it says the cylinder is extended, and we turn on our output cylinder forward. If in the motion of travel, the cylinder goes back, it's no longer going to be extended, and it's going to be retracted. The problem becomes when both these states are either both true or both false. Here the cylinder is neither extended or retracted, but it could also be a faulty cylindricator switch or a broken wire. The logic cannot make a path of logical continuity either extended or retracted, but cannot move forward until one or the other occurs. Here's where we can apply a temporary fix of using not logic. So we have the problem of an ambiguous state because the cylinder is neither forward nor back, so we're not making the limit switch. So one of the things you can do is you can use the NOT logic. For example, for cylinder extend, we're using it's not retracted, and for the cylinder back, we're using the not extended. So if one of these limits becomes true, then the logic gets resolved. And if we move back the other way, again, the logic gets resolved. We can see in this rung there is no logical continuity. The start button has not pressed, does not have a voltage, and therefore the output is not energized. But let's look at the next rung. Here we've run into a problem. For the input stop push button is normally closed and it detects a voltage, therefore it's true. We have logical continuity. However, our run 1 output is not energized. This appears to be conflicting. However, if we go to the next rung and examine it, we find the culprit. Because the stop push button is being used and being examined to look for the absence of voltage, it is a false statement. Therefore, the run 1 is turned off. In situations like these, this is where the expression last order wins comes into play, because both of these rungs are arguing over what to do about run number 1. And since the logic is always solved from left to right down to the next rung, left to right, all too often you will have a duplicate destructive bit. That is, they are both trying to write to the same location, and the last recording in this case is a 0, therefore run is off. It should be noted, there are times when this does not occur. There are several factors contributing to this situation, and you cannot depend on them working in your favor 100% of the time. Therefore, it is best to avoid having duplicate outputs. If you require a particular action to happen or unhappen, clean logic is the best and most reliable solution. When situations like these do arise, there is a cross-reference browser utility you can use to look for duplicated outputs. Let's look at this simple rung of logic the way the PLC resolves it. We see one logical path to the master control relay. We think in relay logic. If the master relay is true, then it's connected and it's one complete path. But to the PLC, there are two completely different viable paths. Let's look at this simple rung of logic the way the PLC resolves it. We see one logical path to the master control relay. We think in relay logic. If the master relay is true, then it's connected and it's one complete path. But to the PLC, there are two completely different viable paths. Let's imagine that the MCR is set because the master start push button has been pressed and released. To the PLC, this is not a viable path because the input is no longer true, so the MCR must be set to 0. But the branch instruction tells the PLC there may be another viable path to logical continuity. So the PLC goes back to the beginning of the rung and tries again. Only during the second pass through, the PLC uses the branch, and this time finds a continuous path and sets a 1 for the MCR. With these two rungs of logic, you can see it will take longer to resolve the second rung over the first rung, since there are many different logical paths for the PLC to use. To the end user, like us, and the process itself, it usually doesn't make any difference. But there are times when branches are nested within branches, and this can slow down the PLC as the scan time gets longer and longer. In situations like these, dividing up the bigger super rung into smaller rungs will help with scan time and troubleshooting, since each rung has a dedicated purpose. In our next video, we'll be looking at adding and clarifying logic by interrupting or enhancing the path of logical continuity. Until then, thanks for watching.